In this video, we're going to discuss several different ways to combine amplification, filtering, modulation, and sampling to recover signals. The simplest receiver you could imagine is attaching a sampler directly to an antenna. This type of receiver is called a direct sampling receiver. It requires extremely high sampling frequencies to accurately capture the input signal, especially if the input signal includes high-frequency blockers, which we're not filtering particularly hard in this architecture. This type of architecture is also wideband, which will admit a lot of noise into the final result. These drawbacks make direct sampling unpopular, but what the architecture lacks in noise performance and power efficiency, because of the power-expensive analog-to-digital converter, it makes up for in flexibility. This captures the whole spectrum, so you can use digital processing to measure signals anywhere in the sampling bandwidth. That means this architecture sees some use in software-defined radios, particularly for lower frequencies. I've drawn an example input spectrum which consists of a single sideband and a blocker. Sampling fast enough means the output spectrum will be identical, though there will be higher frequencies copies that I haven't bothered to draw centered on multiples of the sampling frequency. And when I say single sideband, I mean that the baseband signal consisted of both this shape and its mirror that would live over here, but we've used, for instance, a single sideband mixer to suppress the higher upper sideband. An undersampling receiver deliberately attempts to alias a high-frequency signal to create a low-frequency copy of it. Because we're trying to alias a signal, it's extremely important that the signal be band-limited. This architecture uses a very sharp anti-aliasing filter so that no blockers or other signals get aliased on top of the signal of interest. As a result, this narrow bandpass reduces the noise that's emitted to the undersampling receiver, which improves its noise performance relative to a direct sampling receiver. The output figure in this spectrum shows that the blocker was knocked out by the anti-aliasing figure, and that we have many copies of our signal at high and low frequencies. Filtering out our signal from the nearby upper sideband seems difficult in this example, but small changes in the sampling frequency could make this easier. Undersampling seems kind of magical, but it has a natural time domain interpretation that I think is useful. When you're undersampling, you're measuring the shape of a wave by measuring different phases of the wave in different periods. So if I capture a sample near the start of a wave, I'll wait for a whole period plus a little bit of time to capture the next sample of the wave, instead of trying to sample very quickly and catch that next phase right away. Changing the sampling frequency of this receiver nominally allows it to sample other frequencies easily, but the anti-aliasing filter is difficult to make programmable. As a result, this receiver is usually tied into receiving just one frequency that's defined by the anti-aliasing filter. In a direct down-conversion receiver, we're using a mixer to shift our frequency directly from RF to baseband. These mixers benefit from having both sidebands in the input signal because it doubles the received power. These receivers are very sensitive to IIP2, especially in the mixer, because low-frequency distortion terms will make it directly into the output spectrum. These receivers also have limited programmability because the filtering occurs before the mixer. It's relatively easy to change the mixer LO to look at a different frequency, but the fixed filter means only a small band of signals is available to the mixer, even as you change the LO around. Superheterodyne receivers are interesting architectures that split up gain and filtering over multiple frequency bands, which has a number of advantages. The first mixer in the system is driven by a frequency that shifts our input to an intermediate frequency, or IF. We have one filter at our RF frequency, but it's often a fairly wide filter. Its main job is to limit high-power blockers, but it often admits a whole band of interesting signals. At the intermediate frequency, we have more gain and a very narrow channel select filter. Splitting up the gain over two frequencies can make it easier to avoid instability in amplifiers, which is a nice perk. And having a very narrow filter gives this receiver some programmability. Changing the value of FLO can result in different signals falling into the channel filter. In addition, building a super sharp filter is easier at IF than it is at RF. We can get higher quality components and perhaps use amplifiers to make an active filter. I've put a sampler right after the IF filter, and it may be possible to directly sample some systems with low IF values. However, that sampler is just a shorthand for demodulation, and you could use another mixer to shift the frequency to an even lower frequency, or, depending on the modulation used, you might be able to use asynchronous demodulation techniques on the IF signal. One of the joys of designing receivers is that there are an infinite number of ways to mix and match these receiver design techniques. Here I'm showing an IQ receiver that mixes the input signal to an intermediate frequency, then uses power detectors to find the amplitude of I and Q signals. This just goes to show that you have lots of interesting design freedom in designing complex systems like a receiver. In summary, a variety of receiver architectures exist. Most of them have exacting demands on at least one component in the receive chain, but super heterodynes, which rely on an intermediate frequency between RF and baseband, are very popular.